In the previous episode, we took a look at the proof of concept that we built to kind of hash out any problems that we may run into when trying to build a very large-scale replica of the little Motorola MC14500 chip. And we did run into quite a lot of problems. But the one I want to focus on today is the display. And we were using this very cool little Russian vacuum fluorescent display, but the result register that was being displayed on it was quite dim, especially when compared to the other elements which were being switched on and off from the switches. So that's what I want to do today. I want to take a look at vacuum fluorescent displays. But before we get into it, there's one burning question, and that is, why vacuum fluorescent displays? Why am I not using neon bulbs or Nixie tubes? And when we're talking about vacuum tube computers, I mean, these are the top tier display methods. And well, it all comes down to voltage. Neon bulbs and Nixie tubes are both cold cathode tubes, which means they require a very high voltage in order to excite the gas that's in the tube. So you can't actually run them at a low voltage like we're forcing the regular vacuum tubes that we're using to do. But VFDs don't necessarily need that high voltage. And the ones that we're looking at today, we'll see they have quite a low voltage requirement, which makes them perfect for using with our low voltage vacuum tubes here. But then the next question comes up, is it period correct? Because VFDs were used throughout the 80s and 90s kind of extensively. They were in car dashboards, they were on clocks, alarm clocks, they were on VCRs, microwaves. They were used everywhere. So if we're thinking about 80s and 90s technology, that seems to be a little incongruous with what we're building with vacuum tubes. But it turns out that VFDs were invented in 1959 as an alternative display method for computers. And 1959 is right in the middle of when vacuum tube computers were still being built. As a matter of fact, I think the last vacuum tube computer that was built was like 1962 or 63. So a vacuum fluorescent display is in fact a period correct option. And that's actually what I really love about the Russian VFD that we were using, because it looked period correct, because it had a nice glass tube and the elements were laid out in an interesting fashion. So that's my reasoning behind using a vacuum fluorescent display. And so what I want to do on the bench today is take a look at how the vacuum fluorescent displays are built and maybe try to figure out why we were having the issues that we were having with our display on the proof of concept. So let's hop over to the bench and get started. So first things first, let's take a look at how a vacuum fluorescent display is constructed. And it's actually an incredibly simple construction. There's really only two elements inside of a vacuum fluorescent display. The first is a filament, and this filament often runs at a pretty low voltage. For the ones that we're playing with today, that voltage is 1 volt. And the purpose of this filament is when it warms up, it starts to boil off electrons that kind of hang out right above the filament in a cloud. Now, these electrons don't really have any place to go unless we provide them with a plate. And we need to give that plate a strong positive charge. And in the case of the VFDs that we're going to play with today, that positive charge is 24 volts. And this is for two reasons. One is that's what we happen to have, and so that's what we're going to use. But also that's what the VFD calls for. That's what the data sheet says that these VFDs want to run at, and that's 24 volts on the plate, which is perfect and serendipitous for our needs. Now, if we put a strong positive voltage on this plate, the electrons fly straight up to that plate and get absorbed into it, and the plate is super happy because it's collecting up the electrons, and well, we've got current moving in a circle here. And if this looks familiar, I've kind of given the game away a bit, but this is actually just exactly the same as a directly heated vacuum tube diode. So why does a vacuum fluorescent display illuminate and a vacuum tube diode doesn't? Well, it turns out there's one really important ingredient that I haven't mentioned yet, and that is that the plate itself has a coating on it. And this coating is often zinc oxide. And when these electrons strike the plate, the zinc oxide gets a little excited. And in its excitement, it emits a visible light. And it just so happens that the visible light that zinc oxide emits is colored green. And so that's why so many of the clocks and VCRs and microwaves that used VFDs throughout the 70s, 80s, and 90s all have that exact same green color. So it's just a phosphor essentially coating the plate. And other than that, it's a diode, and that also we can't run electrons in the reverse direction. Now there's also one more primary difference between a vacuum fluorescent display and a vacuum tube diode, and that is that vacuum tube diodes are meant to drive current. They're meant to move electrons around and control other parts of the circuit. Whereas a vacuum fluorescent display is just meant to illuminate, so it doesn't need to move a lot of electrons. So this plate can be really small because it doesn't need to absorb a whole lot of electrons for the rest of the circuit. It just needs to absorb enough electrons to illuminate. And so we've got a really simple VFD here, but it's kind of limited in its capabilities because it can only display on or off. What if we want to display more information than essentially a single binary bit? Well, that's a pretty easy solution. We can actually just add multiple plates inside the same tube. So this is actually what that Russian VFD tube that we're using on the proof of concept is. It's exactly the same as this. And again, it has a really low voltage of just 1 volt for the filament, and we're running 24 volts for the plates. And in this state, the electrons will boil off of the filament here, and they'll just hang around because none of the plates have a positive charge. But if we take one of these buttons and we push it and close it and create a connection to 24 volts, now the electrons have some place to go. So the electrons rush to that plate. And when they strike that plate, the phosphor on that plate gets excited and emits a visible color, a visible light. So that's our indicator. That's one way to indicate. And because none of these others have their switches pushed, they stay off. This is incredibly simple. We can even just push two switches here, make 2 connections, and the electrons will split the difference, and half will go to one and half will go to the other. And so this is a really simple, brilliant way to build interesting displays using low voltage. However, there is one potential problem, and that is using a DC voltage on the filament here. And that's because the filament's purpose is to be hot enough for the electrons from the big power source over here to boil off. But when the filament is over here, it's at just about the same potential as ground. So the filament's not going to be generating enough heat to boil electrons off on this side. So most VFDs would actually run an AC power supply for the filament. Because if you have AC, then you get a consistent heat across the entire filament. By running DC, you get a really high heat here, and you get a extremely low heat here. And so you can end up in a situation where if all of these buttons are pressed, we have a very strong brightness on this side, and then we have a very dim brightness on this side. So you end up with this kind of dimming fade out as you go across. Now, I should say that in theory, that makes total sense, but in practice, I've never actually run into this problem. But that could potentially be happening, so that may be something that we should check out and see what's happening. So I've got a spare one of those Russian VFDs, so I want to go ahead and just plug this into the breadboard and take a look at it and see if we can figure out why we were having the brightness issues that we were having. All right, so I've got my vacuum fluorescent display set up on the breadboard here, as well as 7 switches, and each switch is connected up to one of these 7 plates in here. And it's actually on at the moment, and the filament sits right in front of all 7 of these dots. And it's really, really hard to see because that filament is thinner than a human hair, I swear. And it doesn't glow like a traditional vacuum tube would. It runs at such a low voltage, there's no glow coming out of it. But if you zoom in really close, you can just barely see that super thin filament. But also you can get a good look at what the phosphor looks like on each of these dots. So the heater itself is being powered through this quiet chunky resistor down here. It's actually, actually that's getting kind of warm, huh? This is an 820 ohm resistor. So I don't have a separate 1 volt power supply to power the filament with. So instead what I'm doing is I'm powering the filament off of 24 volts with a essentially large dropper resistor to bring that voltage down so we don't burn the filament up. So we've got the filament on, we've got our switches on. Let's turn a switch, see if we can get it to illuminate. Yeah, there we go. All right, we got that was apparently the top one there. There we go, and that one's in the middle. And man, right off the bat, you can see quite a large brightness difference between the two. Well, let's turn all of them on and see what it looks like. Wow, all right, look at that. So we have 24 volts coming through these 10,000 ohm resistors into the plates of each one of these dots. And you can see that the dot on the bottom here is incredibly dim. And this was actually the same dot that I initially intended to use for the result register. And so that could be the same issue. So it might be due to the fact that we have not enough heat on this end of the filament. So maybe this is the ground side of the filament, and there's not enough heat there, so there's not enough electrons boiling off right in front of that. But we can actually check that pretty easily by just swapping what end of the filament is grounded and what end is pulled up to 1 volt. And so we'll pop our big resistor out here, and we'll pop our ground wire out of the back here. And we'll go ahead and ground the front piece here. There we go. And we'll put our big resistor on the back half back here, which I believe is that pin. Yeah, there we go. All right, so now if this was the ground side before, that is now the positive side, and vice versa up top here. Well, you can see that still only about half of this element is being illuminated. Really, the brightness is maybe just marginally brighter, but we still have that same problem of only about half of the element illuminating. And honestly, I think this is actually just an unfortunate characteristic of this type of really long vacuum fluorescent display. So I'm going to go ahead and swap the resistor back. All right, we got the resistor back, and this is actually a good comparison because you can see that it is indeed a little dimmer down here. So I think that maybe this is actually the negative side of the filament, and that is exacerbating the problem a little bit, but not enough to warrant redesigning the entire heating segment here. And actually this is kind of a small display for something that we're building that's so huge. So I think the solution is going to be, instead of using these for our displays on the big version, we're just going to use maybe something a little different. And I would love to show what I'm intending to use to you guys, but they're not here yet. I've ordered them and they're coming all the way from Russia, but they're not here yet. So all I can really do is just show a picture. And these are essentially the same thing. It looks like the plate is just a big coil of wire, and these look epic. I think they're going to look absolutely amazing as binary 0 and 1 indicators. But unfortunately I don't have them, so we can't really play with them on the breadboard today. But there is one more VFD that I would like to look at today, just because I think it would be fun to look at them. And to explain what that is, let's hop back over to our drawings and take a look at what it is. So that little Russian VFD is really, really cool, and I absolutely love it, and it's fantastic for displaying binary information. But a large majority of the population, myself included, has a hard time reading binary information. So it would help tremendously if we could create a display that can display something that almost everybody can read, and that is decimal numbers. And it turns out you can do this with just the same 7 segments. You just need to rearrange them a little bit into a shape kind of like this. Now, I did my best to draw this as three-dimensionally as possible, but this is essentially the standard layout for a 7-segment display. And that's because with these 7 segments, you can essentially write any number from 0 to 9. And you can actually write most of the alphabet as well. So you could write A, B, C, D, E, and F, and 0 through F would cover a 4-bit binary number, which is great for hexadecimal displays. Now, most VFDs also have one extra component inside of them, and that is a grid between the filament and the 7 individual plates. And this grid can be used for a lot of really interesting purposes. And it actually works exactly the same as a triode. This is essentially a directly heated triode. How cool is that? So you could theoretically have, you got your electrons boiling off of the filament down here, and you could have a sine wave coming into the grid here. And whenever the sine wave is on a negative cycle, the electrons can't flow. So the plates will all turn off. But whenever the sine wave is on a positive cycle, the electrons can flow straight past the grid and strike a plate. And that plate will illuminate. And I think what this is mostly used for in most VFDs throughout the 80s and 90s it was used as a kind of blanking display to control the brightness of the plates. So they would send a pulse width modulated square wave into it, and depending on how long the grid was at a low versus how long the grid was at a high, would control how many electrons can pass past the grid and hit the plates. And a longer time low means that fewer electrons are hitting the plates, which makes them dimmer. And a longer time high means more electrons are hitting the plates, which makes them brighter. So it was often used as a blanking control for the brightness. But there's something really interesting here. Because this is essentially a directly heated vacuum tube triode, you could theoretically feed in an audio signal into this grid, and it would control the amount of electrons that are passing through. And even though these plates are tiny, they can still move more electrons than an original audio signal coming out of a line level source. And so that means that a vacuum fluorescent display like this can be used as a triode amplifier, an audio amplifier. How wild is that? And it's actually been done a couple of times. There's a fantastic channel that I watch. It's called Tanner Tech. And he actually built one of these. He built an audio amplifier out of an old vacuum fluorescent display, essentially doing exactly this. It's an awesome video. And actually his whole channel is a ton of fun. Definitely go check his channel out and watch some of his videos. He's incredibly smart and there's a lot of awesome information over there. But there is one kind of fatal flaw with using a vacuum fluorescent display as an amplifier versus a proper vacuum tube. And that's that, as we said, the vacuum fluorescent display wasn't really meant to move a whole lot of current. So not a whole lot of electrons are meant to flow through a vacuum fluorescent display. It's just meant to illuminate. So the amount of amplification that you can get is very, very limited. So it actually makes a better pre-amplifier than a proper full-on amplifier. I mean, I suppose if you ganged up 100 or so VFDs, you could get some properly good amplification. That would be hilarious. Somebody should do that someday. That would be a ton of fun. Anyways, I digress. This is a really common type of vacuum fluorescent display, and I actually have one of these. It's an IV3 vacuum fluorescent display, and it's a single 7-segment display arranged exactly like this in one tube. So let's pull the breadboard out and take a look at that. All right, here we go. We have that second VFD set up on our breadboard here. And again, we have our same 7 buttons that are feeding into the 7 individual segments. And I also have the grid hooked up on this additional switch over here. So let's flip a switch on and see which one of these segments comes on. Yeah, all right, there we go. So this switch here apparently corresponds to the bottommost segment. And then, yeah, that's the one next to it. There's one up top. There's that one. All right, so now we've written the number 0, and if we flip this last switch, there we go, that's the number 8. And so you can see that by flipping off individual segments, we can change what we're writing. So that we took our 8 and turned it into an A by turning off the bottom segment. That's a P, which you wouldn't really use in hexadecimal. That's an inverse 4, which doesn't work out great there. There we go, that's an actual number 4. There we go, I saw the inverse 4 and I felt this burning need to make a proper 4. But anyway, so now we have our 4 displayed, and I've got the grid at 24 volts now through this 10,000 ohm resistor. So I can actually turn the grid off. There we go, so now the grid is not being pulled high, and you can see it's blocking all of the electrons flowing over to the plate. So we've turned the VFD off, and so I can turn it back on. And so right now I'm just using a switch, but you can see how if this was a sine wave, or if this was an audio signal, you could control the amount of electrons that are flowing to the plate in an analog manner that recreates the audio signal that's being put out. So that's really cool. That's a really epic way to build an amplifier. Not a great amplifier, but an amplifier nonetheless. So there we have it. We have our 2 vacuum fluorescent displays set up on our breadboard here, displaying the number 4 on one and some random dots on the other. But you can see that by controlling which one of these 7 segments is illuminated, we can control what is being displayed on both of them. Now, the final question is, why don't I just use these 7-segment displays? Because they look period correct, because they've got this really beautiful glass tube with a silver getter at top, which looks just like the vacuum tubes that we're using in the rest of the build. But there's a fundamental issue with this, and that is that it's incredibly difficult to convert a binary number to a 7-segment decimal display. There is a massive amount of logic that is required to do that. And when I say logic, I don't mean intelligence. Granted, I'm not smart enough. I would just Google how to do it. I mean logic elements like AND gates and NOR gate. And in the future, I may end up building something like that, but it would end up being probably twice the size of the actual MC14500 that we're trying to build a replica of. It would be extremely intense. But for now, we're just going to stick with the blinking light, and hopefully as soon as my Russian VFDs get here, we can cut the circuit boards and put them in place and see how they look. But in the meantime, that was my deep dive into vacuum fluorescent displays. I hope you guys enjoyed it and maybe learned a little something about VFDs. And I'm having a ton of fun just playing around with these 7 switches here. Oh, hey, look at that. That's actually like a katakana hi, which doesn't really mean anything. It's like a letter in the Japanese alphabet. But that's what it looks like. So anyways, there's lots of interesting things you can do with this. It's a lot of fun. So I'm going to keep playing with this. Thank you guys so much for watching, and we'll see you in the next episode.